they are connected parallel to each other. Parallel to each other, or we can say that the resistors are connected side by side. They are connected side by side. This is the parallel combination. Again the same two resistors R1 and R2. They are connected parallel to each other, means the two ends of both the resistors, R1 and R2. This is one end of R1, another end of R1, one end of R2, another end of R2. So one end of both the resistors are connected together, they are joined together. The other two ends are also joined together. Then we say the two resistors are connected in parallel combination, or we can say they are connected side by side. At the point of joining at one end and the other end, a battery is connected. Here the battery or cell is connected, right? The cell has potential difference V. It has potential difference V. Once again the same thing, in between these 2 points, here we take the point A, point B, right? Now the point A is connected to the positive terminal, point B is connected to negative terminal. So across the point AB, there is a potential difference. That potential difference obviously equal to potential difference across the cell, right? Okay. So let us assume that I current is drawn from the cell, is flowing out from the cell. On reaching this point, on reaching the point A, we are providing the two different paths. There is one basic characteristic of the charges. Whatever be the number of paths are provided, through all the paths they flow. They definitely flow. Here also the two paths are provided. Through both the paths the current will flow. So therefore the current must divide at this point, because we are getting only I current. That has to be divided at this point. So through the resistance R1, current I1, through resistance R2, current I2 flows. After flowing through this resistor, at this point both the current they combine together and forms I current, right? So this is the basic, the characteristic or property of charge. Whatever be the amount of charge released from the cell, the same amount of charge must be reached. So the same amount of current must reach the negative terminal of the cell. That is the law of conservation of charge, right? Here in this, across the point A and B, we have the potential difference V. Therefore, across R1 the potential difference is V. Across R2 also the same potential difference, because both the resistors are directly connected to the cell. Here if we assume this R2 is not present, R2 is absent, then also we can have the closed circuit. R1 is connected across this positive and R2 is connected to negative. On the other hand, if we assume R1 is absent, again R2 is connected to positive, R1 is connected to negative. So that means that both the terminals of both the resistors are connected directly with the terminals of the cell. Therefore, the potential difference is same across the two resistors. Here V1, V and V. Potential difference same. But the current is different. So the total current which is drawn from the cell is equal to sum of the current flows through different branches of resistances. So I equal to I1 plus I2, right? If we simplify this resistance, that R1 and R2, they are combined together, they are providing, the two resistances are providing the opposition. So again we are getting an equivalent resistance. We are getting a single resistance which give the same opposition as is provided by, given by R1 and R2 in parallel combination. This is also the equivalent resistance. We call it is RP, that is resistance in parallel combination, and this also connected across the cell with the potential difference. Again the current I is drawn from it. Now here also we are going to use the Ohm's law, right? Now I equal to, we know the relation V equal to IR, so I equal to V upon R P and V upon R1 plus V upon R2. V is constant. The same potential difference appears across A and B, and that same potential difference is across R1 and across R2, right? P is same. Now if we simplify, 1 upon Rp equal to 1 upon R1 plus 1 upon R2. That means the reciprocal of equivalent resistance in parallel combination, the reciprocal of equivalent resistance is equal to the sum of reciprocal of individual resistances. This is the formula to calculate equivalent resistance in parallel combination. If we simplify it by taking LCM, we get Rp equal to, this is R1, R2 upon R1 plus R2. Upon R1 plus R2, this is the equivalent resistance in parallel combination. Since the reciprocals are equal, here also we can compare Rp with R1 and R2 individually. If we calculate the value, then Rp is less than R1 and Rp is also less than R2. That means the equivalent resistance in parallel combination is less than the individual resistances. In series combination, equivalent resistance is greater than the individual resistances. In parallel combination, equivalent resistance is less than the individual resistances. That means in series combination, the total resistance increases, the equivalent resistance increases. In parallel combination, the equivalent resistance decreases. That we are getting the formula. So these are the two expressions for the series combination and parallel combination. The difference between series and parallel combination, you must be able to differentiate it by taking, if the current flows through all the resistors same, they are connected in series. If the current flows through all the resistors different, they are connected in parallel combination. So in series, I same, V different. In parallel, I different, V same. So this is about the series and parallel combination. Hereafter, we have to solve number of circuits, various types of circuits in which number of resistors are connected in series and parallel. They can be given in mixed combination. In any single circuit, we may have the series and parallel combination. That has to be solved. And then next thing is, we have to calculate the current drawn from the battery. Current flows through different resistance. There are so many things that we'll see in the next session.